Good afternoon, everybody. I'm Tobias Ritschl from the University College London. Great pleasure for me to host this virtual edition of the full paper session, Deep Learning for Rendering, 4 exciting presentations. The first one, without further ado, is called Spherical Gaussian Light Field Textures for Fast Pre-Computed Global Illumination. We have 2 people joining us today. There's Rock and there is Eric, and the presentation will be given by Rock. Rock, the virtual stage is yours.
Hi, I am Rock, and I will be introducing our work on compressing light fields for real-time rendering of global illumination. In this short video, you can see a small preview of the results we get with the method I'm about to describe. To begin with, I'm going to give a little introduction on how light interacts with surfaces in a 3D scene. Following that, there will be a comparison with different methods used to pre-compute approximations for the more complex interactions to be used for real-time applications. Finally, I will be presenting the method we have developed to approximate them, which provides higher flexibility and more visually appealing results. When we see a surface, we are seeing the light reflecting from it. That light can come from 2 different sources, either a light emitter, such as the sun, usually called direct illumination, or from other sources around it that also are reflecting light that arrives to them, called indirect illumination. Light reflecting off of a surface can also be divided into 2 separate components: light that is reflected in all directions equally, usually referred to as diffuse term, and light for which the reflected direction depends on the direction it had when it hit the surface, which we call specular term. Direct illumination is, in comparison, simple to calculate or approximate accurately in real time, both for diffuse and for the specular terms. Indirect illumination, on the other hand, is much more complex, as its definition can be described as a recursive integral over all incident light over all the surfaces, so it is usually pre-computed. The most frequent pre-computation in this regard stores the diffuse term of the indirect illumination in a light map texture. The specular part is, most times, skipped due to its high dimensionality and difficulty to properly compress the usable sizes. The usual approach to pre-compute the specular term for indirect illumination for later use starts by distributing a number of light probes around the scene, points at which the incoming light, what we call the light field, will be captured for all directions around it and stored in some way. Then, when running the real-time rendering application, this pre-computed data is used to recreate the incoming light at that point and in an area around it, with different methods to infer the values that the light would have in any points that lie between 2 or more probes. The most straightforward method to store the light field at each point is to map the surface of the sphere to a surface of a plane and store it as a 2D image, compressing it with any typical image format. This is feasible if the number of light fields to store is small, but it will result in a very lacking reflections for areas with more complex geometry, close light sources, or with smoother materials. It also usually requires manual placing of the sampling points to get any good results. To use more than sampling to get better quality, manually placed points becomes impractical, and the amount of data too huge to actually use. For a sampling grid of 128 by 128 probes, which is 16,000 points distributed on the scene, the amount of raw image data to save, assuming each image is 128 by 128 pixels, is more than 3 gigabytes. To deal with this amount of data so it's usable, several approaches have been taken in the past. One of them is the use of spherical harmonics. In essence, it can be understood as applying a sort of Fourier transform on the spherical function that represents a light field, and taking the parameters for the first few terms. These parameters can then be stored in very little space and used in real time to evaluate an approximation of the original function. The problem with this method is that it can only support lower frequency functions, or it quickly produces artifacts such as ringing. Another method used in some applications has been spherical Gaussians. These are 3D Gaussians restricted so that their center is on the surface of the unit sphere. They are defined with parameters for the 3D direction, a sharpness, and an amplitude, which for light means 3 real-valued numbers. In the literature, until now, the initial approach these have been used is by fixing their direction, so that a predetermined number of Gaussians are distributed around all directions the light can come from. This has similar advantages and problems as the spherical harmonic solution. It can only represent low-frequency information unless the high frequencies are aligned with the axes of some of the Gaussians, and it does not interpolate too well between sampling points. Our proposal is to use spherical Gaussians, but to also optimize the direction each one points to, allowing them to represent more details in the light field that would have been shown if the directions were fixed. It should be evident that optimizing these Gaussians with free access becomes much more expensive. We also have as a requirement for the method that one of its properties should be that interpolating the values that recreate the light fields between two sample points should give us a plausible intermediate light field. By default, if we apply an optimization algorithm on the parameters for the set of Gaussians for each light field, such as gradient descent or expectation maximization, we are likely going to find different solutions for each light field, which will give us Gaussians that are very much not interpolable between two sampling points on the scene. This is not only because there might be too much detail in the light field to be represented by fewer Gaussians, so that they might end up pointing towards different directions, but also because they are going to be interpolated in order. That is, the first Gaussian on one sample point will be matched with the first Gaussian for the other sample points. This means that not only the solution should be similar in directions, it more importantly has to keep the order in which the Gaussians are distributed over the sphere. Typical attempts at solving this problem involve adding an extra step between each iteration of the optimization algorithm used, that tries to push Gaussians in the same ordinal position for adjacent sampling points towards their average direction. Using this method, the first thing one encounters is that changing how much the direction is pushed together in comparison with how much the optimization step moves these positions is critical to getting better or worse results. Of course, by applying this counterforce to the optimization, it takes much more time to reach convergence. Using this method, as can be seen, still creates artifacts. These are produced when points and their neighbors reach a good enough solution so that their sorting of the Gaussians spreads in an area around them. When that area encounters a similar one from a distant set of neighboring points, but the Gaussian's directions between the two zones are dissimilar, a ridge appears where the pushing together step can't overcome the intermediate error that would appear when trying to change those directions. Instead, to solve the optimization problem, we take another path. We define a function that, given a light field as its input, will give the parameters for a set of Gaussians approximating that light field. This function could have many different definitions, but we would like that it be simple to define, evaluate, and obtain its parameters. For the generating function, we use a convolutional neural network, for its simplicity, as well as for the multiple tools already existing to optimize them. Since deep neural networks are biased towards learning lower frequency functions, as shown by the work from Rahman et al., we expect that the interpolation between outputs for similar input light fields should evaluate to a plausible light field for the intermediate sampling point it would correspond to. This is an overview of the architecture for our network. It has several convolution layers that bring the input values from 128 by 128 by 3 channels image to a 16 by 16 by 256 tensor. This is then passed through fully connected layers, and in the end, this output a number of parameters equal to 7 times the predefined number of Gaussians. A network like this is trained for the scene for which we want to compress the light fields, using each precomputed light field as an input and in the error function in the output. This is done by sending the input light field through the network, which produces a set of values that are interpreted as parameters for spherical Gaussians. The sum of these Gaussians is then compared to the input light field, and the error between them is backpropagated through the network. In our test, we have found that a network trained for a specific scene generalizes to other scenes. As can be seen, the images generated with this method do not suffer the artifacts we encountered in the previous optimization method. This produces good interpolation between 2 points in the scene. One technical advantage that this method has over straightforward optimization of the Gaussian parameters is that each new light field fed to the network will usually help improve the results for other inputs. This means that the total time to obtain an optimized set of Gaussians for all the points barely increases when doubling the number of sample points in the scene, while it would be doubled for the straightforward optimization of the parameters of each sampling point. In the plot, we can see that stochastic gradient descent produces comparatively poor results judging by the MSE, while taking a lot more time. Expectation maximization reaches a lower MSE much sooner, but we can also see that, as expected, increasing the number of sampling points increases the time to convergence linearly. Our solution can be seen to converge around the 4-hour mark in these test cases, 64 by 64, 128 by 128, and 256 by 256, or 4,000, 16,000, and 65,000 sampling points respectively. In comparison, EM takes about 4 to 6 hours to converge for 16,000 points and around 25 to 30 hours for 65,000 points. As I said previously, one of the requirements is that we can use the method in real-time applications. Spherical Gaussians with fixed directions were already being used in some applications, so this advantage remains. For actual numbers, the 16,000 samples of the scene data's raw data occupy several gigabytes. Once processed with this method, can be represented in a few megabytes. We have found 16 Gaussians per sampling point to give sufficient good results. In terms of speed at runtime, with 16 Gaussians we get a rendering time per frame between 1 and 2 milliseconds. We have done tests for 32 and 64 Gaussians too, and with our unoptimized implementation, rendering the scenes presented with 64 Gaussians per sampling point takes from 3 to 5 milliseconds per frame. These render times make this method totally compatible in regards to speeds required with demanding applications such as virtual reality. Here, the results can be seen to represent reflections very well, even for more glossy materials, including a comparison of 16 Gaussians and 64 Gaussians. One of the issues with the method, as hinted at earlier, is that the precomputation step takes a significant amount of time to execute. First, it requires precomputing the light field values to compress, which takes from 3 to 8 hours in our test cases, for grids of 128 by 128 sample points and 512 by 512 sample points respectively, using an RTX 2080 card for both steps. Even though the method can be used on relatively smooth surfaces, two mirror-like surfaces will not present good reflections from indirect illumination. A possible solution for this could be to use more traditionally used methods for real-time specular reflections on mirror-like surfaces, but still use our method in the reflected surfaces. An additional contribution to improve visual accuracy is by applying the method from the work by Hayes et al. And combining direct illumination with stochastic shadows. This provides a way to use the environment map of the scene in the reflections instead of having it compressed by the Gaussians. In short, when precomputing the light field for a sampling point, we also keep a map of the visibility from that point to the environment map, convolved with the BRDF of the surface that point belongs to. The light field in this precomputation does not represent the environment, although it uses it as a light source when calculating light coming from other sources. This convolved visibility is then compressed in a similar way as the indirect illumination. When used in the real-time application, the reflected direction on the surface is used to sample the environment map, preconvolved to account for the material's BRDF, and that value is multiplied with the reconstructed visibility. This is then added to the reconstructed light field. More details on how this is accomplished can be found in our paper. In this short animation, the stages and result of applying our method are shown. Diffuse illumination is incorporated from a light map. Global illumination reflections from the surfaces in the scene are added. Reflections from the environment map are added while taking visibility into account. Altogether, gives very nice results that run in less than 2 milliseconds per frame. And with this, we reach the end of my presentation. We will now be answering questions.
Thank you. Fantastic. Rock, I received there might be no questions so far on the YouTube channel and also not on the Discord one. So everybody tuned in. I'm actively checking. While I'm doing so, I will start with a few questions at that point. So there's a couple of other papers in the session that do somehow similar things. They also fit neural networks to something useful in rendering. They go a slightly different way. You choose those Gaussian mixtures, which is kind of a cool idea and like an interesting topic, but why don't you have the neural network doing the entire job altogether, like from the beginning to the end? Gaussian mixture models angular dependency, so the network could also be queried by something that depends on angle. What made you choose? What convinces you so much that this intermediate Gaussian representation is the right thing?
Well, doing that so you would try then to execute the neural network in real time. And yes.
In the same way you're evaluating the Gaussians, this thing would evaluate the neural network. Gilles, in the last talk, and also the other one, surprisingly, these do kind of similar things. They solve different problems, probably. This is not so much interactive graphics, but it's also not something you could not probably do.
Yeah, we had some attempts on doing that. Our first attempts on that, we found that it wasn't too fast, or as fast as we wanted it to be. So we chose this approach at first because it was much more easy to get it to run at real-time speeds.
It is fast, so this it delivers. It is fast, and once you have this representation, that is great. So Eric probably wants to say.
Yes, am I
wrong?
Great, yeah. So I mean, obviously that's an interesting solution. David Lubke showed a few hours ago some amazing NVIDIA work where they did exactly this, but then they're talking so far about a second per frame, and we're currently looking for stuff that you could actually use in real time today.
Yeah.
So there's several orders of magnitude difference in the speed.
Yeah. So it is the speed, this intermediate thing that's super good. So let me check if there are further questions. I think probably not at that point, at least not on YouTube. Is there one? Yeah, Discord notifications. That's another thing. We'll find out. Probably it's on your guys' side sometimes too. The other question that I would have, we have a bit of time left. What was it? Yes, exactly. People have been using an entire zoo of different kinds of mixture models of different kinds. So you choose this particular one. There was a progression of SIGGRAPH Asia papers that is, well, there's quite some papers. Is there benefit in going for some more complicated representation, or are you convinced that this most simple one, which works very well and is fast, is the end of the story, or could you believe to make it anisotropic and all these other crazy things people kept doing?
So we think that there's benefit in looking into more complex representations. This was the simpler one to use, because it uses few parameters, so it's easy to compress in very few textures, and it's easy to get a network that optimizes for it. More complex representations require more complex computations also in real time. So we are looking into that, but we haven't yet. Basically, we are looking into anisotropic and other functions that could also be used in representing such incoming light.
Okay, so unless I'm wrong, do you guys see questions that you want to answer on any of those channels? Because I don't. I think there are none at this point. So people, please do ask those questions. In some way, authors will also be around after this to talk to. So don't be shy. Let's have this as real as we can in this virtual setting. No questions, you think? Okay, good. So I think there are none, right? Okay. So then I think it's time to move on to the next paper. Thank you, Rox. Thanks, Eric, for that great work. Thank you. Okay, let me consolidate my stuff here. Next paper, if I have that right, is John, are you on, John? This is neural temporal adaptive sampling and denoising. So from this super trendy topic of doing all kinds of denoising, making lots of things from very few samples. I heard about this work from John before, so I'm very excited to see the complete picture now at that point. So authors are John Haslegreen, John Munkberg, Marco Salvi, Anjul Patney, and Aaron Leffon, and all of them are from NVIDIA. It's yours.
Hello, my name is John, and I will present our work on neural temporal adaptive sampling and denoising. Our main goal is that we want to help enable real-time Monte Carlo rendering, or at least get the field closer to real-time. The image to the right is rendered using 1024 paths or samples per pixel, and it has pretty good quality. But in real-time we can currently only afford to render around 4 samples per pixel, as shown in the image to the left. So we need an efficient way to bridge the quality gap between these two images. Typically, this is done by applying an edge-aware denoiser to the noisy input samples, where the denoiser is helped by a few G-buffer guides, such as for example normals and depth. There are of course many types of denoisers, but recent work has shown great promise in DL-based, deep learning-based denoisers, so that is what we will focus on in this work. When working with low sample counts or real-time, temporal data reuse is critical, as can be seen in the video here, with a single-frame denoiser in the middle flickering a lot. Temporal reuse increases effective sample counts, as the samples can be reprojected between adjacent frames. But interestingly, it also automatically helps stabilize the output images, even if we just train the network based on the error of a single image. Before looking at our algorithm, we'll see how some previous work handles temporal reuse in deep learning. Chaitanya proposes to use a recurrent autoencoder consisting of an encoder part on the left here that compacts the data into a bottleneck, and then the data is once again expanded in a decoder part. Temporal reuse is handled by having a small memory cell or RNN on each hierarchical level of the encoder. The good thing about this design is that it only operates on a single input frame at a time, which means that it can be made pretty fast, and it can also support infinite reuse or history. The main challenge of this approach is that the network needs to learn how to reproject the data, which actually turns out to be a very hard task for the network. In another approach, Vogels et al. Process a number of frames in parallel, then reproject the intermediate data to the time of the output frame, and the final denoised result is generated through an additional neural network. The benefit of their design is that they used fixed function reprojection, so the network does not need to spend capacity learning the reprojection operation. The downside of their approach is that they work on multiple frames in parallel, which tend to make the network expensive, and they can also not support infinite reuse or history. Our solution is very simple but combines the strong points of both previous work. We see the denoiser network as a black box, and then we use an external feedback loop to handle temporal reuse. This means that we can pretty much replace the denoiser with any type of network we would like. The temporal reuse is handled by reprojecting the denoised output of the previous frame using motion vectors computed by the renderer, and concatenating it to the input data for the current frame. The input data is shown to the upper left, and it can be, for example, noisy input samples and a few G-buffer guides such as albedo or normal. This is a recurrent type of network design, pretty similar to Chaitanya et al. So we must train it on a clip of frames rather than a single frame to allow the internal state to settle. Again, we get the best of both previous work here, with the network operating on a single frame at the time, which is good for performance, and the reprojection being handled by fixed function code, which tends to help training and improve image quality. Okay, so we went ahead and implemented the system by plugging in a unit as the denoiser network, and we actually saw pretty good performance and quality out of it. But something that became apparent pretty quickly is that it's actually a bad idea to do uniform sampling when doing temporal reuse as well. So on this slide you can see 2 consecutive frames from an animation clip, called them frame n and n+1, And if we look in the area indicated by the green arrow here, you can see that here it's actually very easy to reproject data between the frames. There is relatively little movement, there is no animation, there is no disocclusion or anything. But if we look in the area indicated by the red arrow, we can see that this is occluded in the previous frame and the object is moving around a lot, so it's probably hard to reproject data here. And in this case, it makes a lot more sense to use some kind of adaptive sampling strategy, placing more samples in these hard areas. And here we can draw some inspiration from previous work. So Kuznetsov et al. Propose a method for performing adaptive sampling in the deep learning framework. So what they do is they uniformly sample an image first. They send the uniformly sampled image into a sample map estimator network that is responsible for generating a sample map or sample density map. And this map dictates to the renderer how many paths it should send for each pixel. The result then will be an adaptively sampled image at the target sample rate, say for example 4 samples per pixel. And this image is then sent into a denoiser network, and the final result is generated. And they train this entire system end to end, meaning that they only optimize for the error of the final result. In order to do so, you must be able to backpropagate through this whole pipeline, which means that you must also be able to backpropagate through the renderer. Fortunately, this is a special case because it turns out that the gradient with respect to sample count is quite easy to compute and depends only on your sampled image and the reference image. This is what our final architecture looks like when we incorporate their adaptive sampling strategy into our network with temporal reuse. So you can see we have the same denoiser network, the same temporal feedback loop that we had before, and we have added a block here in the middle to implement adaptive sampling. Just like previous work by a sample map estimator network that computes a sample map or sample density map that is used by the renderer to generate an adaptively sampled image. The big difference between this and previous work is that we have no initial sampling pass. Instead, we feed the sample map estimator with just G-buffer guides from the current frame, such as normal, depth, etc., and the final denoised output of the previous frame, but temporarily reprojected to the time of the current frame. And the thinking here is that wherever the temporal reprojection is successful, the final denoised output is a pretty good guide of how many samples we would want to send to a region. And wherever the reprojection fails, then we don't have any temporal reuse anyway, so we are likely going to want to sample these areas pretty densely. And the additional information given by a 1 sample per pixel initial sampling pass is actually quite low. Okay, so now that we've covered the system overview, let's have a bit more detailed look at the denoiser network. So the denoiser network is a unit which is pretty similar to what Chaitanya used in their work. So the unit consists of an encoder part shown on the left here, and the encoder is essentially a cascade of 3x3 convolutions followed by downscale operations. You can think of this pretty similar to how you would build a MIP hierarchy of an image. Then you have a bottleneck in the middle, which is just a single convolution, and the decoder part. And the decoder part once again expands the data to the input resolution. This is done through upscale and convolution operations. Our network uses kernel prediction, which means that instead of directly predicting the denoised color, it waits for a filter that is applied to the noisy input samples to produce the denoised image. Kernel prediction has been shown to improve image quality, but the problem is that we need very large filters for denoising. So to improve performance, we use what's called hierarchical kernel prediction. And this is the reason why we have 3 different outputs from the network, shown in green below here, and they occur on 3 different hierarchical levels of the decoder. Hierarchical kernel prediction essentially approximates a large filter kernel by applying many small filter kernels on different MIP levels and combining the result. To round off the architectural description, let's look at some benefits we get from combining temporal reuse and adaptive sampling. The first thing is that we can entirely skip the initial sampling pass and instead just estimate the sample density from G-buffer and history. And this, of course, means that we can allocate the entire sample budget towards adaptive sampling. This actually works a lot better than we initially anticipated. So you can see in the top row here, we have sample maps for our architecture evaluated on a few different scenes. And these are standard heat map encoded. So a cool color like the dark blue here indicates a low number of samples, and a hot color like red indicates a higher number of samples. We can see that the sampling behaves pretty much as expected here, with a higher number of samples dedicated towards the edges. And you can see that the sampling has found the highlight in this faucet here, as well as the shadow in the sink. And if you compare this to previous work, Kuznetsov et al., which used one sample per pixel uniform initial sampling pass, you can see that the noise of the initial samples really hurt the quality of the sample map. Another benefit from adding temporal reuse is that adaptive sampling goes from just meaning whether we have high geometrical or shading complexity to also incorporating where can we temporarily reuse data into the mix. So if we look at the sample map in the middle here, you can see that just as expected, we can still sample spatial features such as edges really well. But in the left of the image here, we have a region that is disoccluded in the previous frame by the wall in front of it. And we see that the network learns to put more samples in this region, which makes sense. And then we also have features that are both spatial and temporal, such as the specular highlight and the shoulder here. And because the specular highlight is view dependent, it's not completely possible to reproject it, so it makes sense to place more samples around these features. To evaluate our network, we trained on the 9 animated scenes shown in this slide. Most of the scenes were already available to us, but to make the motion a bit more complex, we added some random skin meshes to them. There are between 16 and 25 clips from each scene, totaling about 1,400 frames. And the reason that we use clips is that we need to train on consecutive frames to get the temporal reuse correct. To further augment the data, we use standard augmentations like random cropping, color shifting, reflection, and rotation. Then to evaluate quality, we use the 3 test scenes shown on this slide: sun, temple, classroom, and bathroom. There is no overlap between the scenes in the training and test set, but as you can see, some skin meshes appear in both. As our dataset is quite limited, we did some holdout studies, where we hold out one scene and train on the rest, to verify that the network actually generalizes, but please refer to the paper for more details about that. Okay, so now for some results. I'll only show visual results in this presentation, so if you want error metrics, etc., you will unfortunately have to refer to the paper. I'll start off with what's actually a very hard scene for us. And the reason this scene is hard is that it contains many mirror surfaces, such as the mirrors on the wall and the robot. The reason that they are hard is because the motion vectors is computed at the first bounce. So when you see an object through a reflection, the motion will be incorrect, and therefore the reprojection will also be incorrect. But still you can see on our adaptive denoiser here that the result is pretty good quality, and it's also very temporally stable, even as seen through the mirror. Especially when you compare it to the input samples down left here, where you can see that the noise level is very high. If you look at the sample map in the center, you can see that it's also very stable, and it detects the features that you would expect it to detect. And you can see that it even detects the robot in the mirror here, even though there are no G buffer guides helping it for the same reason that the motion vector is wrong. Here is another comparison, this time on the classroom scene, which seems like a pretty easy scene, but if you look closer on the input samples here, you can see that they are actually very noisy. And the reason for this is that we're lighting the scene with a high-frequency light probe, so most of the light is actually indirect. In this case, we're comparing the recursive autoencoder by Chaitanya to our network, and in this case we're using the uniform network, so we're not enabling the adaptive sampling part. This is to make the comparison more fair, since a recursive autoencoder doesn't use adaptive sampling. And here you can see that the recursive autoencoder still struggles with a lot of temporal noise, while our network does a very good job. And the reason for this is that it's actually very hard to learn the reprojection operator, which the recursive autoencoder has to do. And we gain a lot of quality by just having a fixed function reprojection operator, and then having the network just learn where the reprojected data is correct or incorrect. This is an image quality comparison between our algorithm with adaptive sampling and our algorithm with uniform sampling. So the benefits of adaptive sampling is particularly noticeable in scenes where you have a concentrated geometric detail and that are otherwise quite uniform. So you can see in this case we get a lot of better quality on the back and the wings of the statue, which are quite blurry in the uniform version. Interestingly, the temporal aspects of adaptive sampling are not as noticeable as we first thought, because when you look at an animation, you don't tend to look straight at or gaze track areas with disocclusion. So even if the noise is higher here, it's not that noticeable. I will round off with some artifacts and failure cases. Going from left to right, we have the same issue that every other denoiser has, that if our input samples don't contain enough information, we'll end up overblurring or losing detail compared to a reference image. Then in the middle, we've noticed that our network tends to err on the side of reusing data too much temporally. So in this case, you can see that the chair is bleeding into the background. And on the very right, we still have some issues with low frequency noise, especially if we have difficult shading or very large noise in our input samples. And in this case, it looks like the specular highlight is boiling. With that, I thank you for your attention and leave you with a real-time path tracing demo that NVIDIA showed last SIGGRAPH. It's been continually developed and now runs at about 40 frames per second with a stripped-down version of our denoiser using about 7 milliseconds per frame.
Good. John, thank you. Thanks for this exciting talk. I'm happy to see the noise is gone. I think there are no questions again on the channel if I did it right. So no, there are questions. So let me read this. Let me read the question. I will first ask the question myself, then I will read the question, and then we will probably have the question or not. I was just wondering, there's always the same question that I had also to all those other denoisers, and I wasn't quite sure what's the right thing. So I asked you again. Now you do this over time. Do you warp only the RGB, or have you considered also warping the internal activations in some way?
Yeah, so
ongoing debate.
Yeah. We've done very simple experiments. So we've tried using a larger internal state. So it's still a full resolution, but we added more features to the output and let the network reproject this and then use it as input for the next frame. And there are no restrictions on these features, so it's just the 3 first that are evaluated as a color, and the rest are the. We didn't really see much benefit from it in this case. It's not entirely. I'm not entirely sure why, but it seemed to scale about as much as adding more features to an internal layer of the network. One kind of theory is that the output image is a good estimation of the reference, and the reference would be a good guide for the next frame if you were to reproject it.
It makes sense because the image was what the features were made from, so it does not contain anything that you can't maybe recreate, so it doesn't have any additional information. It's not like you drop the blue channel or something like that. On the other hand, it could save computation, so it's still open, and I think if we see more denoisers, we might get more clear on that.
Yeah.
I'm very happy that we do have questions. I think I will pick the second one from Sebastian Weiss. He's asking on the Discord channel. So how do you avoid the importance map not simply learning to allocate more samples everywhere? Why does it localize that somewhere? What pushes the network to be clever and not just sample?
Yeah, so we need to constrain it to a target sample count, basically. So the sample density map is always normalized to a total sample count. And this actually has a lot of problems, like intricate problems when you train the network with stability issues and these sort of things. But by restricting the total number of sample counts, you can pretty easily make sure that the network just doesn't put in a lot of samples everywhere.
Okay, I'm not sure if the answer was pleasing that person, but then on Discord, you're free to voice if you want to ask more or iterate the question. There also was the question on how the derivatives are made in respect to sample count. So I think that's previous work. I think that's this EGSR paper, Ramamurthy group, like one of your key citations. And I think they did the math and they had lots of clever tricks and it can be done. It's not your contribution, is it?
Yeah, no, it's not our contribution. And it turns out to be fairly easy because initially you might think that you need to backprop through the entire rendering engine, but when you just backprop with respect to sample count, it turns out it just depends on the reference image and the noisy input image, and the derivative is just proportional to the difference between those.
Good, like great idea in the original paper and super cool extension we see here. Another question I had was, it kind of assumes every ray costs the same, in the same way like it assumes every ray is contributing in some similar way, or maybe there's some more contribution to the denoising and to the variance that might be different. So have you considered also including like how much it costs to actually send the ray, and or doesn't it differ anymore with modern ray tracers? I'm not maybe up to speed.
No, I haven't, but it's a really good point because it differs a lot based on materials, etc. So it would actually be interesting to include that. I'm not entirely, I don't have it on the top of my head how you would do about it, but it would be, yeah.
Yeah, so I think there's no further questions and we're super good on time. If this is this, there's a lot of virtual applause as you hear. Thank you, John, for the exciting talk. Yeah.
Thanks.
Okay, then we move to the second part of the session where we have two, if you guys allow me to see this like that, similar papers. Both of them are concerned with BRDF/BTF modeling. And the first one, if my ordering is correct, would be deep BRDF, a deep representation for manipulating measured BRDFs. We have Jay Guo-Ji today with us, who would give the presentation. The work is done at the State Key Lab in Nanjing in China, and the IQI Intelligence also from China. So we're excited to have you here virtually. Please go ahead.
Hello everyone, I'm Jie Guo from Nanjing University. It's my great pleasure to present our recent research work on manipulating measured BRDFs using deep learning. Material appearance is an important topic in computer graphics. Throughout the years, many works have been devoted to capturing, modeling, or editing material representations in order to convey a realistic appearance. Currently, these representations are mostly analytical. These analytical models are specially designed to capture high-frequency gleams, multiple scattering, surface bumpiness, or even wave effects. Despite these successes, analytical appearance models are still limited. The appearances that can be modeled are restricted by the scopes of the underlying analytical expressions. To reflect the appearances of real materials, measured BRDFs are preferred. Recently, an increasing amount of data from real-world materials have been created. A measured BRDF is essentially a list of measurements for different camera and light positions. To faithfully encode the original appearance, a very high sample rate for the BRDF is usually required. Although more accurate by definition, Measured BRDFs from a high memory footprint and a significant computational cost stemming from the storage and processing of massive BRDF data. This makes either editing or manipulating measured BRDFs quite difficult. Therefore, lots of previous methods try to reduce the dimensionality of the measured BRDF to facilitate its usage. Matusik and his collaborators proposed to perform BRDF dimensionality reduction by either linear analysis or nonlinear dimensionality reducers, resulting in a 45-dimensional or 15-dimensional manifold. Nielsen et al. Improved the traditional PCA by employing a log relative mapping on raw BRDF values and achieved better linear compressions for measured BRDF data. To allow intuitive editing, Serrano et al. Established the relationship between a handful of high-level perceptual attributes and the PCA coefficients of measured BRDFs. Sun et al. Proposed a diffuse specular separation strategy for measured BRDFs and suggested to perform PCA for the diffuse part and the specular part of a BRDF separately. However, these previous work all apply linear dimensionality reducer to measured BRDFs, which is efficient but requires a large number of components to reproduce the original BRDF with high fidelity. Another widely used strategy to lower the complexity of measured BRDFs is to fit the data to simpler analytical models. For instance, we can fit measured BRDF data to some famous analytical models, such as the Wall model, Linform model, or the Lanforge model. However, as you can see here, there are some problems. First, the fitting process is often time-consuming and numerically unstable. And second, in some cases, they may be not accurate enough to represent faithfully certain appearances, as the case here. Inspired by the success of convolutional neural networks, in many fields, we proposed deep BRDF, a deep learning-based representation to explore the low-dimensional subspace of real-world BRDF. Our network is an autoencoder which can explore a nonlinear low-dimensional manifold. The basic idea is to design a deep autoencoder to explore the low-dimensional latent space of measured BRDFs. Currently, we train our deep BRDF with mirror BRDF dataset. Several graphical applications can be benefit from deep BRDF. We demonstrated two here: BRDF editing and BRDF recovery. Once training is completed for deep BRDF, two additional subnetworks, namely a fully connected neural network and a CNN, are connected to the decoder to perform BRDF editing and BRDF recovery, respectively. Now, we show the network architecture of deep BRDF. Each measured BRDF is reorganized as a sequence of image slices and then fed into our network. In this network, 3 2D convolutional layers with kernel size 3 by 3 and stride 2 are used to downsample the input data. 3 residual blocks are inserted to improve the performance of learning. To extract the low-dimensional latent vector, a fully connected layer is employed. To decode the latent vector, we expand this vector with another fully connected layer, followed by 3 deconvolutional layers. We know that raw BRDF data usually contain high dynamic range information. This means the magnitudes of input values can be arbitrarily high, which causes problems for most CNNs. We use this formula to compress the HDR data. For our autoencoder, the goal is to recover the compressed high-dimensional BRDF data with minimal reconstruction error. The intuitive idea is to use L1 loss or L2 loss. We found that L2 loss is superior to L1 loss. Here we compare the visual effects between L1 loss and L2 loss. From the comparison, we see that L2 loss generally surpasses L1 loss both qualitatively and quantitatively in our network. The network output generated by L1 loss is slightly biased. Here is the geometric interpretation of deep BRDF. The proposed deep autoencoder tries to project the original BRDF data, the cross-scale, in the mirror dataset to the latent low-dimensional manifold, where these examples concentrated. One can think of the low-dimensional latent vector, the dots here, as a representation of the original BRDF, which is well suited to capture the main variations in the data. Now, let's see the reconstruction quality comparison of our deep BRDF against PCA and improved PCA of Nielsen et al. The visual comparisons reveal that synthesized images using BRDFs reconstructed by traditional PCA deviate greatly from the reference images, even if the dimension of the underlying subspace is high, due to the inherent linearity and high dynamic range of the original BRDF data. Improved PCA of Nielsen et al. Significantly improves the traditional PCA both visually and in terms of relative absolute error. It converges quickly as the dimensionality increases and achieves satisfactory results in a 40-dimensional subspace. However, our method based on deep BRDF can achieve high quality reconstruction even if the underlying manifold lies in a low-dimensional subspace. This diagram reports all the reconstruction errors of the materials in the mirror dataset as compared with two PCA-based methods. Clearly, our method outperforms IPCA on almost all materials when the dimensionality is equal. We also compare our method with Sun et al. For each BRDF, we assign 1D for its diffuse part and 9D for its specular part in the method of Sun et al. Although it further improves the IPCA, it is still inferior than our deep learning-based solution, especially on the materials with changing color or complex lobes. We further show the benefit of the proposed deep BRDF with the following two applications. That is, measured BRDF editing and single image BRDF recovery. For material editing, once we get a low-dimensional representation of a measured BRDF based on deep BRDF, the next point is how to bridge the deep BRDF and some intuitive material properties that are convenient for BRDF editing. We achieve this goal with a shallow, fully connected neural network to map a handful of material properties to the latent vector of BRDFs. Now, let's see some results. Here are the results of linear interpretations between two measured materials in mirror dataset. The interpretation is conducted in a low-dimensional space. We compare the spaces of IPCA and our deep BRDF. As seen, our deep BRDF supports smooth and perceptually linear changes when interpolating between a very specular material and a diffuse one. IPCA yields strange artifacts when the dimensionality is low, and sudden changes in appearance even if the dimensionality is high. Here is the result of editing the diffuse albedo of grain plastic while keeping other attributes unchanged. Let's see how the appearance is changed. Here we edit the roughness of red plastic and compare our method to Serrano et al. Our method achieves small smooth transitions as shown here, without color shifting. We also make a comparison between IPCA and deep BRDF as a low-dimensional representation in BRDF editing. We observe that BRDF editing based on IPCA is unable to guarantee smooth transitions between BRDFs. The perception of glossiness may fluctuate strangely as shown here. There is also color shifting problems. Again, our method based on deep BRDF provides both smooth transitions and high physical fidelities. The second application facilitated by deep BRDF is single image BRDF recovery. In this application, we try to infer material from an input image. Similar to material editing, once the previous autoencoder has learned a latent representation for measured BRDFs, our goal becomes how to bridge the input image and the latent representation. The way is that we train another CNN which learns to map an input image to the latent space of this autoencoder. This CNN takes as input a 256 by 256 color image, which is then passed through a series of 3 convolutional layers to max pooling layers and 2 fully connected layers. In training this network, L1 loss is used as the loss function. The training examples are synthesized by some virtual things. Now, let's see some results. Here we compare our method with the method of Ye et al. In recovering homogeneous BRDFs. Note that the method of Ye et al. Can only handle planar material samples. Therefore, for a fair comparison, we only use images rendered with a planar plane in this figure. The results tell that our method achieves high recovery quality on these synthesized examples. Here are more comparisons of real-world pictures. Again, our method shows higher reconstruction quality than that of Ye et al. In conclusion, we have presented the deep BRDF, a deep learning-based representation for measured BRDF. We have applied the deep BRDF to edit measured BRDFs. We also applied it to the task of single image BRDF recovery. Thank you.
Thanks, that's great. We're fortunate because we do have a couple of questions this time. I have to mute my audio. No, I made the mistake. But I saw the people talking on the chat. So the question from the chat from Derek Bradley is a question that I also had. You have presented L1 loss, L2 loss. You want to get the signal right. You achieve success using that to some level. But what people usually care about, and it's a very open discussion in BRDF community, isn't it the image in the end? Shouldn't the error be defined for some geometry, for some illumination, and then SSIM or something like that on the image? Can you comment on that? Can you help resolving that?
You mean in the second application, right? In the BRDF recovery, right?
In both. I would say in every instance you're using a loss, and the loss, as we understood, I think as Derek understood, and as I understand it, is L1 between reflecteds.
Yeah, actually, in the deep BRDF, we are trying to recover the BRDF data itself, not the rendered image in the training the deep BRDF. So there's no lighting the geometry in this stage. But
yes, in the understand you do this, but in the end, you're not looking at reflectance values per se. You're probably going to use it in a rendering task where you do make.
Actually, in training the deep BRDF, we do not use any rendered image. Actually, we use BRDF slice itself. So we actually want to reconstruct the BRDF slice. We see each BRDF as image sequence.
Yep.
We don't actually render the image, render the BRDF. in this
Okay,
stage.
that's an answer because there's different schools how to do this, and you clearly positioned this as being in this school, which is valid. I mean, if you want to have accurate reflectance, then maybe that's what you're looking for. That's cool. Gilles, who's giving the next talk, was so kind to give us another question that makes sense. It was voted up on Discord, so at least 2 people have this question. Is your input data resampled in any form, or can you directly use as it comes from Merle? I'm not sure what you're assuming or what Gilles was assuming. So what kind of resampling or reformatting does it involve?
Yeah, we resample the Merle dataset into actually for the Merle dataset we use its original size 90 times 19 times 180, the original size of the Merle dataset.
Okay, I hope this answers. Gilles, your approve of this answer? I think it does. Okay, good. There's another question, like a very direct one, wasn't mentioned in the talk. I'm sure you will have it in the paper. Murat is asking, what's the rendering time here? If you have an analytic model that will have maybe 6 parameters in Phong, it will render in like no time. Now you have yours. So can you comment a bit what the performance, will we ever use it in a game in any time soon, or is it too costly still?
Yeah. You mean if we use deeper BRDF in a rendering scenario, right? Yeah. So if we want to use it in rendering, we have to decode the latent vector, right? Yeah. But actually, the decoder is very, very fast because the network is not very deep. So actually, the decoder part is very fast.
Yeah, I do believe. I think I read it's 3 levels, so that would need to access, maybe it's sparse access, I think, which is the problem. You have to access many pixels to then feed them into some levels of convolution, and doing this random access. I think there was there's other papers.
Yeah, right.
I think. Cool. So then I had a question, if I didn't miss anything else, but let me say what was my question. It took me some time to understand that you start with a stack of images and then you describe the size of your 2D convolutions, and then I was confused, like, why aren't you using 3D convolutions or more 4D convolutions? So can you confirm it's not convolutional along the other direction? Is this an active choice? Did you really decide to do it like that? Or is it more that the other thing, sorry, you couldn't get it working, or you didn't think about it? So why only this? Why this?
Yeah, actually, we have tried the 3D convolution, but the network is not very good at not converge very good. Maybe for a 3D convolution, the network have to redesign them. But when, we have claimed in the paper, actually the image slices are quite similar. If we use 2D convolution, we actually can use very few image slices, BRDF slices. Even one slice can reconstruct 4 BRDF. I think it's the benefit of using 1D convolution.
Okay. I'm trying to make sense of a question that Valentin is also asking. We would have time for a bit of a questioning still. I will read it out and maybe you can make sense of that. So he's thanking you for the presentation, and he says he didn't understand very well how you connected the properties to the latent space. Properties, so what is properties? Latent space, I know. So can you make sense of that question?
Yeah, you mean how to connect the property to the latent space, right?
BRDF properties. So can you give an example of what that would be? I would not immediately know what he means. Diffuse, roughness, specular, these kinds of properties, these natural attributes that you would assign to something, do they manifest in some reasonable way in latent space? Do they group or something like that?
Yes, the property can choose a different set. Actually, we use specular color, diffuse color, and roughness. Very simple properties. Very simple properties to do material editing. Actually, other properties is also work, I think.
Then he asks another question that many people have when it comes to representing BRDFs with neural networks, and I think I have a similar question. So is this in the end more expressive, or what's the benefit? You have 8 parameter Phong, it can do a limited set. Now you have 40 parameters, it probably can do more, but what evidence do you have it's worth it? Do you have this one example that any PCA something can't do, or is it really more expressive?
Yeah, I think so, because actually we want to find the non-linear representation of the measured BRDF. PCA is linear, right? So I think the actual space of the measured BRDF should be on a low-dimensional non-linear space. So that's the motivation of our project.
That's clear that it's more expressive than a linear basis, but then before that there are some handcrafted, very clever models which clearly are not linear. Even good old Phong is not a linear basis, I think. Yeah, so it has a non-linear effect how you choose your glossiness. So would you be confident that this is with 40 parameters more expressive than most of these analytic models? Yeah, good. There's lots of questions. I think Valentin is going on. I'm not fast enough to decipher this. Plus, we're out of time. I think we're thanking you again. Everybody thanks you for this excellent talk. And we're moving on to the next one, which is, as I remember, Gilles, but I have to get up the paper to be reminded of all the authors, which, of course, I all know, but I have to get the order right and the title. So next talk is called Unified Neural Encodings of BTF. The presentation will be given from Gilles Reiner. He's from University College, as I am. It's Abhijit Ghosh from Imperial College, Wenzel Jakob from École Polytechnique Fédérale de Lausanne, and there's Tim Weyrich. It says in the proceedings, it's an H in the end. He also goes by the name of Weyrich, so don't be confused about that. Gilles, it's yours.
Hi everyone, my name is Gilles, and I will be presenting our paper on unified neural encoding of bidirectional texture functions. The aim of our paper is to render materials with complex appearance. Traditionally, there's two major approaches to rendering materials in computer graphics. Analytic models rely on a concise mathematical expression with specific parameters to control the appearance. They are generally very efficient in size and memory, but it can be hard to accurately reproduce existing materials. Data-driven or image-based models, on the other hand, directly interpolate from real-world measurements to drive the simulated appearance. This makes them flexible and faithful to represent existing materials, but they can be tedious to handle because they rely on a lot of data. Our goal is to find a representation for real-world materials that is somewhere in between and combines advantages from both approaches. Our starting point is the most exhaustive image-based material representation, the bidirectional texture function. Intuitively, BTFs can be seen as a stack of 2D textures of the same material on the different lighting and viewing directions. At rendering time, these textures are interpolated for all angular configurations in the scene and mapped onto the object geometry. The more measurements in the dataset, the better the simulation, so BTFs often contain tens of thousands of textures. This is a huge memory requirement, so many approaches have been proposed to deal with it. BTF representations can generally be divided into two classes. The first one is based on matrix factorization, which means the resulting representation is still a set of discrete tensors. Techniques include principal component analysis, clustering, hierarchical tensor decomposition, and vector quantization, and so on. The other type of approaches is based on fitting continuous functions. Previous work has experimented with polynomials, spherical radial functions, and in the most generic form, mixtures of parametric BRDF models. Typically, analytic models have a harder time approximating the original data well, so often a residual of the fit is kept and factorized separately. Recently, the rise of deep learning has witnessed its applications to reflectance modeling in different forms. Deep appearance maps are networks used as continuous reflectance models, parametrized on viewing and normal directions to learn the appearance of a material. Networks can also encode distributions of radiance in scenes, such as for light field rendering or for image-based relighting of scenes. Finally, networks have also proven themselves capable of learning global light transport for effects such as ambient occlusion or subsurface scattering. Given that a BTF is basically a database of examples of one material's appearance, and since neural networks have proven to be good approximators of radiance distributions, last year our team in Reiner et al. 2019 introduced a neural representation for BTFs that offers unprecedented compression rates in conjunction with a natural interpolation between angular BTF samples. In that approach, each material is represented by a set of only 10 latent maps compared to the original 22,000 textures, and an associated decoder network, which is continuously parametrized on light and view directions and implicitly handles the angular interpolation. We can draw an analogy with parametric BRDF models by comparing the latent maps to the spatially varying BRDF parameters, such as diffuse and specular albedo maps, normal maps, and so on, and comparing the decoder network to the chosen BRDF model, for instance, Phong, Cook-Torrens, or GGX, etc. In their pipeline, individual texels, which are different spatial points on the material, are processed separately. They are fed to an encoder network that projects each texel to a latent vector. This compact descriptor is then used as input parameters to the decoder network, along with view and light directions. Similarly to a parametric BRDF, the decoder outputs an RGB reflectance value for the given inputs. And if we gather all the texel descriptors in their original spatial arrangement, we obtain the latent parameter maps, which are equivalent to SVBRDF parameter maps. This means that encoding a new BTF requires training a new network. Also, the latent maps do not exist in the same space. Each set of latent maps is specific to the associated decoder network. We, in turn, would like to have a single decoder so that the latent maps all exist in the same latent basis. There would be a single pre-trained decoder network, and all materials would be encoded in the same latent space, which would open doors to many interesting applications and optimizations. Converting a new BTF would then only be a matter of evaluating the encoding pipeline, which takes seconds, rather than retraining a full network, which takes several hours. However, this makes the whole task a lot harder, because our network needs to generalize well to materials unseen at training time, instead of being overfitted to each new material. An additional difficulty arises because BTFs can have different formats. Depending on the data source, the number of textures, of angular configurations, of viewing and lighting angles is not necessarily the same. Our approach needs to be flexible to accommodate any possible dataset structures. So now, our focus is on the encoding strategy. Reiner et al. Showed that their decoder achieves good interpolation and good approximation results, so we operate in the same paradigm. We process each texel separately and project it to a vector that serves as parameters to a decoder that has the same architecture as Reiner et al.'s material-specific decoder. We are looking for an encoding network that can learn to convert any texel to a latent descriptor. To recap, a BTF texel is essentially a list of RGB reflectance measurements with the associated light and view angles. We need to be able to process texels from different BTFs with potentially different structures. This means we cannot make any assumptions about the length, n, of the list of measurements, nor about the specific angles in that list. This makes a deep learning approach complicated with standard architectures. Traditionally, fully connected layers require a fixed length of inputs, and convolutional layers commonly process inputs that lie on a grid-like structure. The angular BTF measurements, however, can be placed in any arbitrary arrangement on the hemisphere, depending on the BTF scanner. So how do we approach this? We start by considering the contents of a texel as 3 signals, the R, G, and B channels, parametrized on 4 dimensions, 2 spherical angles for the view direction and 2 for the light direction. Let's simplify the problem to 2 dimensions by fixing the view direction for now. and let us switch to the continuous setting for a moment. These here are 2D slices of the continuous reflectance profile of two texels from different materials. We would like to find filters to integrate these signals against in order to project them into a feature basis. This means integration over the angular domain of the product of the signal with the filter. Back in the discrete setting, this would mean element-wise multiplication with the filter values at the sampled angles, followed by averaging. To better integrate with the rest of the pipeline, we choose to learn these angular filters using a multi-layer perceptron on the right side here. This MLP takes a light and view configuration as input and returns the value of each filter kernel at the given angular positions. We query this MLP at each angular configuration that was sampled in the input texel and perform element-wise multiplication with the expanded texel. The resulting matrix is averaged and unrolled, and its dimensionality is further reduced with fully connected layers and rectified linear units. This encoding strategy can deal with any input format, that is, any angular resolution and any sampling pattern, in any given ordering. The full encoding pipeline produces the latent vector that describes the texel. This latent vector serves as input to our unified decoder, which is a standard fully connected network, the same architecture as Reiner et al.'s per material decoder. The encoding network, the angular MLP, and the decoder are all initialized randomly and trained jointly as an autoencoding pipeline. For training, we use datasets from the currently biggest publicly available BTF database, which comes from the University of Bonn. It contains BTFs from 84 materials, organized in 7 semantic classes. Each dataset contains textures of 400 by 400 pixels, viewed and lit from 151 directions, which amounts to over 22,000 textures in total. We train on 11 out of 12 materials of each semantic class, keeping a total of 7 materials unseen during training. For more details on architecture and training, we refer to the paper. All the results we will show from here on use the 7 validation materials. In this figure, we show one texture from each BTF, corresponding to one sampled combination of light and view directions, but keep in mind that we have tens of thousands of textures in the original datasets. We first show what would happen if we took Reiner et al.'s per material network in the same conditions as our network. That means trained on the same database and applied to unseen materials. The approach visibly would not generalize well at all. When a network instance is trained per material, however, the reconstruction is very accurate because the network overfits to that material. We view this overfitting situation as an upper bound for performance and compare it to our network evaluated on unseen materials. We use the same compression budget for both architectures, meaning the same number of 8 latent dimensions and the same size and architecture for both decoder networks. The reconstructions of our network are slightly degraded compared to the per material network, but overall the visual fidelity is very high. Considering that we directly convert unseen materials just by evaluating our network, the improvement gained with the per material network via hours of overfitting a new network instance is marginal. The textures in the original BTFs are the only proper ground truth that we have access to, because as soon as we render, the sampled values in the original datasets must be interpolated. Nevertheless, it makes sense to also compare renderings, because they show the performance of the methods on the entire view and lighting hemispheres, not only at originally sampled positions. For our reconstruction quality to be on par with the per-material network, we found that 32 latent dimensions is a good compromise. The difference obtained by increasing the latent dimensions is quite subtle and most visible on materials with fine specular highlights. By increasing the dimensionality of the latent descriptor, we allow for more fine appearance variations and reduce the blurring effect. The comparisons are even more striking on the animated point light illumination. Datasets with lots of spatial details and contrast are generally encoded well by our network, as well as with the per-material network. On this stone dataset, our reconstruction almost has more contrast than the per-material network that was overfitted, because there is more intermaterial appearance variation and our network generalizes better. This shiny fabric, however, poses more of a challenge for our network as it exhibits a lot of anisotropy and specularity. There are not many examples of satin-like fabrics in the training set. Similarly, the specularity of this wood dataset tends to be slightly more blurred by our network, but overall our visual fidelity is still very high. To prove the resilience of our network to different angular samplings, we also evaluated on BTFs from a different data source, in this case the UTIA BTF database at the Czech Academy of Sciences. These datasets have a 4 times lower angular sampling than the Bond datasets, but our network still produces good results. To further evaluate the robustness to different angular samplings, we take a look at what happens if we only input a subset of the original angles in the texel. We can see that the reconstruction converges very quickly. With only 5% of the input angles, the reconstruction error is stable, meaning we could take only 1,000 textures instead of the 22,000 in the original BTFs, and we would obtain the same reconstruction quality. So the encoding is robust, but what about other positions in the latent space? We visualize what happens if we perform spatial interpolation in the latent domain before running the latent vectors through the decoder network, rather than in the final decoded textures. The difference is barely noticeable, which shows that the latent space is also well behaved in between positions that were queried during training. This means that MIP mapping, for instance, can be applied in the latent domain, and the decoder only needs to be run once per reflectance query. This also means that the latent space can be used for texture synthesis. Synthesizing textures using the original BTF is very tedious because of the high number of images. Using the latent maps, however, we only need to synthesize a 32-dimensional texture rather than a texture with tens of thousands of channels. In this case, we used standard image quilting in the latent domain to produce these renderings. To conclude, we presented a unified version of the neural BTF. Now, representing a BTF in this model is only a matter of evaluating the encoding pipeline. We don't need to perform a new training procedure for every new material, which lasts for hours. Additionally, unifying the latent space and the decoder comes with many advantages and opportunities for optimizations. Since we only use one universal decoder network, it can be optimized for faster rendering, and also MIP mapping and texture synthesis can be performed in the latent space. One thing that is still limiting us is the relatively sparse amount of publicly available BTF data. For deep learning, you would ideally like to have hundreds or thousands of materials. We also envision that the unified latent space and the single model that we propose will allow for BTF editing in the latent domain in the future. Thank you very much for listening, and I'm happy to take any questions you might have.
Lovely, Gilles. Thanks for this talk. I think there are no questions at that point, so I will start with one. I asked one question somebody else had on the previous paper, okay? Is it convolutional? I mean, I asked this before, but there also has been this question. So now you explain there's order invariance and all of these things. You learn those MLPs, but is this a convolution in any sense then in the end, or is it something else? I'm puzzled.
So there's no convolutional layers. That there's only fully connected layers. But I guess you could somehow view the integration against the kernel filters as some kind of convolution over the whole angular hemisphere.
Yeah, that was what confused me. So it has properties which are similar to a convolution. You have something like a kernel with which you're weighting your observations. But then is it correct that you're not shifting this thing? Or like, is this a function that is defined on the entire hemisphere? Or is it something that changes when you take different pairs? So then it starts to be a lot like a convolution. Or does it more like sit like a nonlinear basis function in space for a certain angle and doesn't move? This confused me. I thought I understood, but once you talked, I lost it again. So,
right. I think, so I guess the best way to view it would be just there's a fixed number of channels in that function that the angular MLP learns. So basically it would be like a convolution over the whole hemisphere with this fixed number of channels, and all the channels of that kernel, so all of the dimensions of that kernel, so it's a fixed function for each of those dimensions. So it's I guess you could view it as a convolution that is not shifted, basically. So each dimension of that kernel just represents a different filter.
Okay, so that's quite open. Also in this point cloud, deep point cloud processing community, it's quite an open question, like what you should do, how convolutional it should be, if it should be this or should be that. So I read the paper and also saw a few details. So there's one thing that I found quite interesting. Is it correct that you're permuting the color channels to do data augmentation? Because somebody just suggested that to me and I said that's a pretty bad idea. So is it, or can you do it? I really want to know. So analyze this a bit. It sounds okay now that I see it, that you did it.
Yeah, so I guess empirically it works for us, at least. So in my case, it made the performance a lot better, especially before using this trick. Sometimes the hue was a bit off in the reconstruction, and since doing this sort of cheap augmentation, the hue is pretty much spot on. So in that sense, it helped. But I guess it depends a lot on how you pre-process your data and what format you use and what the network actually does. So maybe it's not a good idea in every case.
Now that you did it and you did it successful, I believe it. I will have to think again. Probably if you have a low number of training examples, then it will cost you a bit. But at the same time, augmentation is so valuable that it's probably a good idea to do it.
That's where it came from. We were thinking about some way to augment the data a bit, because there's 84 materials in total, so it's really not that much for a bigger network. So yeah, that's how the idea came about.
Makes sense. So again, there was a question on rendering performance in Google, in YouTube, I think. Can you comment on that?
So the rendering times are we didn't insist on that a lot in this paper, because the decoder, so the part that you use for rendering, is basically the same as in the previous Eurographics paper. But in this case, so we have in practice we have 32 latent maps, so 32 scalar latent maps. So we just look up one vector in those latent maps and then run it through 4 fully connected layers of 106 neurons each to get the RGB value of the BSDF at that point, which doesn't take very long, but it's still slower. It's still not real time. But just to give a number, we compared it for a given scene to rendering with a diffuse texture, just a single diffuse RGB texture, and it was about 5 to 6 times slower. So there is some overhead in evaluating the decoder network, but it's not that much slower. So it's basically the same order of magnitude.
Good, similar like the method before, similar footprint, I think. So we're on the right track. There's some work still to do.
Yep.
I think this concludes the session. There are no further questions that I see at that point. Thanks, Gilles. Thanks to all the other presenters. I hope this is officially the last time we have to do this virtual. I hope you will all enjoy the conference, and yeah, have a lovely afternoon. Bye-bye. Thanks, everybody.